All right. Welcome back, class. This is Mr. Somerville here, continuing to talk probability with you this week. So far, we've really explored conditional probability, and we've taken a closer look at two-way tables. Today, in lesson 10.2.3, we kind of pull that together. We're looking at conditional probability. We're also looking at what it means for events to be independent or associated again, and we'll be using two-way tables to do this. So, jumping in, today we're actually only doing 92, 93, and 94, which have some pretty good content to them. 92 is a two-way table problem that has you thinking about what it means to be independent or associated, and exploring the relationship between a two-way table and an area model. And then 93 actually goes back to one of those spinner games that you liked so much from Chapter 4. We'll be using that to formally introduce the multiplication rule, which is the equation that we've been using because we saw it in an Edpuzzle video to calculate conditional probability, but here we're introducing it through our text and then using it in 94 to look at one more way to tell if two events are independent from one another. So at this point, take a look at 92, 93, and 94. You have the answer key to guide you along the way. It has some really good help, but we'll still come back together and recap as soon as you finish the lesson. So please pause the video right now and go ahead and do the lesson on your own, and then I'll see you back when you're done and we'll talk about some of the key ideas. All right, guys, good luck. And welcome back. So hopefully this lesson went well. We'll just talk quickly together to make sure that you've seen all the main ideas. For 92, we were given information about freshmen who were exercising or eating fruits and vegetables, and you were asked to make a two-way table for that. Instead of me redrawing it, let's rely on what we already have given here in the answer key, because they've set that up much nicer than I could draw that on my own anyway. So if we look, they've created a two-way table that has exercise or do not exercise in the columns, followed by eating fruits and vegetables or not eating fruits and vegetables for the rows. They filled in the information they had. Remember, you could use the outside of this two-way table to help you check the sums of the inside rows and columns, because they do have to add to that. For example, 0.25 and 0.08 have to add to 0.33, and then down along the outside, 0.33 and 0.67 have to add to 1. 0.35 and 0.65 have to add to 1. So those are the facts you use to fill in missing values for any two-way table you're working with. Once you have that two-way table filled in, you can start to answer questions B, C, and D. So when they ask what the probability is that a freshman in this study exercises regularly and eats 5 servings of fruits and vegetables each day, you just need to find that area in your two-way table. So you look for exercise, you look for eats fruits and vegetables, where they overlap. I see there's a 0.25 decimal written in there, which means there's a 25% probability that you do both of those if you're a freshman. In part C, asking the probability that a freshman in this study exercises regularly or eats 5 servings of fruits and vegetables each day, there's a little more to it. We could look at the 3 boxes that line up with either of those, which would be to exercise, which has 0.25 and 0.1 in it, or eat fruits and vegetables, which goes to 0.25 and 0.08. The trick here, if we want to add those together, we don't add 0.25 twice because it's only there one time. So if we add 0.25 plus 0.10 plus 0.08, that will give us the correct probability, which ends up being 0.43 or 43%. The other way would be to use the addition rule, which would be to add the probabilities of each and then subtract their intersection. So you have 2 different options to find that union. Here is technically what we're finding because it's an OR situation. For D, we're asked, do you think that a freshman who ate 5 servings of fruit and vegetables per day is more likely to exercise? And what that is that's saying, hey, are these events independent or are they associated? So we need to look at, okay, is the probability of one equal to the probability of that event given the other? And if you do that, the answer key actually shows this. They say, okay, the probability of exercise does not equal the probability of exercise given fruits and vegetables, because 0.35 which is the probability of exercising, is not the same as 0.25 over 0.33, which is the probability of exercise given fruits and vegetables. You could also flip it around and do it the other way and have event A be probability of fruits and vegetables and B be exercise, but the result is still the same. You see that those events are independent of one another. In 93, which was the spinner problem, let's look at that quickly. So the double spin game, where we're given a spinner, they tell us that that $100 sector takes up 1/8 of the circle. We're assuming that that's a right angle between 10 and 5 there. So it looks like 100 is 1/8, $1 would be 3/8, 10 would be 2/8, and 5 would be 2/8, or 1/4 each. So those are the probabilities we'd be working with. And they say, okay, make an area model to show the sample space of every possible outcome for 2 spins. So if you make that model, well, again, this is when the answer key started. They didn't fill the complete model in, but as it loads here, you'll see they've set up all the structure we really need. So they've created an area model just like we used to, with the values and the probabilities on the outside, and then you can multiply them to get the probability of both events happening on the inside. So that's what we're looking at. They've just put the probabilities in there for those events that are winners, because you have to spin the same thing twice to win. And that's really what you need when you're answering the questions regarding double spin here. So using that model, you really should be able to get the answers to those questions. Like in B, Nick comes home and he tells Zach that he won some money in the double spin game. So we know he won money. What we have to do is find the probability that he won $100 given that he won some money. So the probability of 100 given the win would be that 1 over 64 probability divided by the probability of winning, which is the sum of all those winning options. And that's how you get to that 1 over 18. By the end of this problem, they've introduced the multiplication rule, which says that P of A given B is equal to P of A and B over P of B. And that is what we've been using already because we had that head start from Edpuzzle, but now we've really formally been introduced to it in our textbook. That helps us in 94 to come up with another definition for independence. So in 94, just a reminder what the problem looked like, they have us kind of figuring out, okay, how did the multiplication rule get its name? So rewrite it starting with A and B. So let's do this one. We'll actually write it out. So for 94, they want us to rewrite things. So instead of what was originally given was probability of A given B, and I'll use that symbol there, was equal to the probability of A and B, which is an intersection. So instead of writing and, we could use that upside down U there. I got to double check that because I know previously in a video I spent the whole time calling it a union, when since it is and, it is an intersection. And then that's all over the probability of event B. So that is the original multiplication rule that was introduced in the previous problem. They gave us the instructions, hey, we have to start with P of A and B on one side here. And so basically, that just means do an inverse operation. To get it by itself, we would multiply by P of B on both sides. And that just rearranges it to be the probability of A given B multiplied by the probability of B. So this is a rearranged version that we can call the multiplication rule. This was part A. In part B, they say write the relationship between event A and event B for when they are independent using symbols. So we want a relationship between event A and event B if they are independent, not associated. So to do that, we'll write that the probability of A given B, because they're independent, can be equal to the probability of event A, because A given B is no different than the probability of A, just A, if they are truly independent. So that's part B. And then lastly, part C tells us, jumping back over, that we are supposed to substitute the independence relationship from part B into the multiplication rule to get another definition for independence. So if we look back at our new multiplication rule and do some substituting, well, when you see P of A given B, you can actually replace it with the probability of A. So now we can write that the probability of A and B is equal to the probability of A multiplied by the probability of B. This is a really powerful tool because now we have another way to determine if two events are independent. So that's if two events are independent. We'll actually use this quite a bit. It's a convenient way to check and say, okay, is the intersection equal to those two separate events multiplied together? And then that's how you can tell they're independent. Hang on to these thoughts, hang on to your work that you did today, because we will be continuing with this lesson and the review and preview, but just to stay within our time frame we're allowed. I think that's all we really had time for in today's lesson. If you have any questions, please shoot me an email and let me know, and I'll get you an answer as soon as possible. All right, good luck, guys. Oh.